Think modern locomotives burn diesel fuel just like they did in 1950. Think again. Right now, in 2024 and 2025, railroad engineers are testing electric locomotives powered by overhead wires and hydrogen-fueled trains that emit nothing but water vapor. While we focus on electric cars and hydrogen buses, we've overlooked the fact that railroads are quietly revolutionizing how they power freight movement. Today, you're going to discover how electric and hydrogen trains are transforming American railroads from coal-burning machines into clean, efficient transportation. Get ready to understand why the future of freight might be powered by electricity and hydrogen instead of diesel. This is the story of how trains are going green. For 170 years, American trains burned fossil fuels. Steam locomotives burned coal. Diesel locomotives burned oil. That era is ending. In 2024, Switzerland deployed hydrogen trains on regular service routes. India launched its first hydrogen train. Russia is testing hydrogen-powered rail buses. Meanwhile, American railroads are quietly experimenting with electric locomotives and hydrogen systems, preparing for a future where freight trains operate without petroleum. In the next few minutes, we're going to explore 5 ways that electric and hydrogen technology are reshaping American railroads. This isn't utopian thinking. This is happening now. This is the story of how trains are solving environmental challenges that seemed impossible a decade ago. The hydrogen train, how water vapor replaces diesel exhaust in September 2024. Russia completed its first hydrogen train, a passenger vehicle powered by hydrogen fuel cells that convert hydrogen and oxygen into electricity, with water vapor as the only emission. Switzerland has already deployed hydrogen trains on regular service, replacing diesel-powered trains on routes where electrification isn't feasible. These aren't prototype vehicles. They're production trains operating on established railroad lines carrying passengers daily. What makes hydrogen trains special is that they deliver the range and power of diesel locomotives without the emissions. A hydrogen train can travel 500 miles on a single tank of hydrogen. It can accelerate quickly, climb grades, and move freight with the same capability as diesel engines. The refueling process takes 15 to 20 minutes, comparable to diesel refueling. For environmental engineers, hydrogen represents a solution to decarbonization that doesn't require rewiring entire railroad networks. Countries and railroads can deploy hydrogen trains immediately on existing routes. Historical data from operating hydrogen trains shows that maintenance costs are comparable to diesel locomotives. Reliability is excellent, and passenger and freight operators report satisfaction with performance. The technology works. The hydrogen supply chain, building infrastructure for tomorrow. Here's where the real challenge begins. Where does the hydrogen come from? Modern hydrogen production relies largely on natural gas, which creates its own emissions. But newer production methods exist. Electrolysis uses electricity to split water into hydrogen and oxygen. If that electricity comes from renewable sources, wind, solar, hydroelectric, then the hydrogen produced is genuinely clean. What makes hydrogen infrastructure special is that it's being built right now across North America. Private companies and railroads are constructing hydrogen production facilities adjacent to major rail corridors. Wind farms in Montana and the Dakotas are producing electricity that powers electrolysis systems, creating clean hydrogen for trains. By 2030, industry projections estimate that sufficient hydrogen production capacity will exist to power all North American freight trains if they converted completely. For energy engineers, hydrogen infrastructure represents a convergence between renewable energy and transportation that solves multiple problems. Simultaneously, it uses renewable electricity that otherwise goes to waste. It provides a storage mechanism for renewable energy, and it powers transportation without emissions. Electric locomotives. When trains run on overhead wires, long before diesel locomotives existed, electric trains operated on overhead electrical lines. The first electric trains appeared in Europe in the 1890s. Europe electrified thousands of miles of railroad. America chose diesel instead. Now that choice is being reconsidered. Modern electric locomotives powered by overhead catenary wires are far more efficient than diesel locomotives and emit zero carbon. What makes electric locomotives special is their operational efficiency. Electric motors convert electricity to motion with 90 to 95% efficiency. Diesel engines operate at 35 to 45% efficiency. An electric locomotive can move the same freight using less than half the energy required by a diesel locomotive. Running costs drop dramatically. Historical data from European railroads that electrified shows that operating costs per ton-mile decreased by 40 to 60% compared to diesel operation. The capital cost of electrification is substantial, roughly $1 to $2 million per mile. But the operational savings recoup this investment within 10 to 15 years. For railroads, electrification makes financial sense even before considering environmental benefits. The electrification challenge: miles of wire across the country. Here's the obstacle: electrifying America's 140,000 miles of railroad would require stringing overhead wires across mountains, deserts, and remote areas at enormous cost. The infrastructure investment would exceed $100 billion. No single railroad has the financial resources to undertake electrification independently. This is where federal support becomes critical. The Infrastructure Investment and Jobs Act allocated billions for railroad electrification. States like California, which is building high-speed rail, are planning complete electrification. Freight railroads are experimenting with partial electrification of major corridors. What makes electrification special is that it's a long-term investment that yields benefits for decades. A railroad that invests in electrification today will enjoy cost savings for 50 years. But the initial capital requirement is daunting. Historical data from European railroad electrification shows that when governments and railroads share infrastructure costs, electrification proceeds rapidly. Switzerland and Austria have electrified over 75% of their railroad networks, achieving nearly 100% carbon-free freight and passenger service. For American railroads examining electrification options, the European example provides a roadmap for what's possible: the battery electric train. When trains carry their power source, not all electric trains require overhead wires. Modern lithium-ion battery technology allows trains to carry their power source on board. A train travels its route, powered by onboard batteries, then recharges at terminals. Battery technology has improved dramatically. Modern railroad grade batteries can deliver sufficient energy to move freight. Trains across 100-plus mile routes on a single charge. What makes battery special is that it allows electrification of routes that don't justify the cost of overhead wires. A lightly used branch line can operate battery electric trains without infrastructure investment. A freight line that doesn't carry high volumes can use battery-powered locomotives economically. Battery technology is improving rapidly. Manufacturers project that battery costs will drop 40% by 2030, making battery electric economically viable for nearly all railroad applications. For railroad engineers, battery electric represents a transitional technology that can bridge the gap between fossil fuels and full electrification or hydrogen deployment. The environmental impact: how trains becoming electric transforms. Carbon emissions: American freight railroads burn roughly 3 billion gallons of diesel fuel annually, producing over 30 million tons of carbon dioxide. If those diesel locomotives were replaced with electric or hydrogen alternatives, American transportation carbon emissions would decrease by 3 to 5%. That's meaningful. That's transformative. Historical data from transportation carbon analysis shows that electrifying freight railroads would reduce American carbon emissions more than electrifying all passenger cars combined, because trains are inherently more efficient and carry vastly more cargo. What makes this special is that the solution exists and is economically viable. We don't need revolutionary breakthroughs. We need investment and political will. European railroads have proven that electric and hydrogen trains work. American railroads have demonstrated technical capability to operate these systems. The remaining question is simply whether investment will follow. For climate scientists and environmental engineers, railroad decarbonization represents one of the highest leverage climate solutions available: high impact, achievable with existing technology, economically viable. The jobs question: will railroad workers benefit, or suffer? A legitimate concern: will transitioning to electric and hydrogen trains cost railroad jobs? Historical data from European railroads that electrified suggests no. Job totals remained stable. Work shifted from diesel locomotive maintenance to electrical system maintenance. skilled workers transitioned to new roles. Wages remained comparable. For labor economists, railroad transition to clean energy demonstrates that technological transition doesn't necessarily mean job loss when managed properly. What makes this special is that railroad jobs are skilled positions that pay well. A person who spent 20 years maintaining diesel locomotives possesses mechanical knowledge applicable to electric systems. Retraining programs can update skills. Railroad operators report that workers prefer electric trains because they're quieter, cleaner, and safer to maintain than diesel locomotives. For American railroad workers, electrification and hydrogen transition represent opportunity rather than threat to opportunity to work on cleaner technology and opportunity to participate in solving environmental challenges. The timeline. When will this actually happen? Major American railroads project that 20 to 30% of their fleet will operate on electric or hydrogen by 2040. By 2050, the projection increases to 60 to 80%. This is gradual transition, but it's accelerating. Pilot projects are operating now. Infrastructure investment is increasing. Technology reliability is proven for railroad industry analysts. The transition is not a question of if, but when. What makes this timeline special is that it's aligned with climate goals. If America is going to reduce transportation carbon emissions as required by climate commitments, railroad decarbonization must accelerate substantially. But the technology exists. The economics make sense. The regulatory environment supports transition. The main variable is investment rate and political commitment. Electric and hydrogen trains represent more than environmental solutions. They represent the evolution of railroad power from the fossil fuel era to the clean energy era. What's remarkable is that trains are leading this transition, not following it. Railroads are pioneering battery and hydrogen technology that's finding application in trucks and buses. The innovation you see on trains today becomes the standard for all transportation tomorrow. The next time you see a freight train passing by, remember this: that train might be powered by diesel today, but within 20 years, its replacement could be powered by hydrogen or electricity. American railroads are going green, and the future of freight transportation is cleaner than anyone imagined possible a decade ago. If you've enjoyed this story about how trains are transforming to meet environmental challenges, please like this video and subscribe for more stories about the future of railroad.